our next speaker here on stage, Takaya Nakagawa, if I hope
yes, that is
to
correct.
have spoken that correctly.
Perfect.
He's from a researcher from NTT in Japan, and we are very proud that he took the long route from Japan to here to come to our conference.
Is it? Yes, yes.
Okay, so please welcome him with another warm applause here on stage. We are ready. The talk is yours. Thank you.
Thank you. Guten Tag. Ich bin Nakagawa. Sorry, this is the only word I know, so let's keep going. And I'm Nakagawa. I'm working with a company called NTT Advanced Technology. And let me briefly talk about what I do at the NTT Advanced Technology. I'm in the team with optical product division, and my team develops and manufactures and sells manufacturing equipment for the tools for optical connectors, connector cleaners, and other optical-related items. And as you can see, we specialize in optical communications, and I'm based in Germany, but we do have office in. I'm based in Japan. We do have office in Germany, though. Okay. Well, now let me give you a brief introduction of optical connectors. You might probably already know, but optical connectors are components used to connect, disconnect optical fibers. It must be able to connect an optical fibers accurately at low cost to allow for the mass use and ease of use so that anyone can use them. And today, I'd like to introduce some new problems that have been arising as the speed of optical communication increase and how to deal with them. Let's start by briefly talking about the Ethernet standards. This graph shows the Ethernet standards. The standards has been completed up to 800G, and with 1.6 and 3.2 is also inside. High-speed communications between GPU servers are also essential requirement for the generative AI, which we hear often. As such high-speed Ethernet standards are being proposed every day, but optical connectors are always used for the transceiver interface of each standard, making optical connections unavoidable. With these optical connections, new problems are becoming apparent as the communication speed increases. Today, I will focus on the problems of the communication errors caused by the return loss. Recently, we have been receiving more and more inquiries about unknown communication errors from our customers. We often heard that communication error occurs after replacing higher transmission rates such as 100G from the lower transmission rate. We guessed the cause of the error could be the return loss of optical fiber transmission line because return loss is specified in IEEE standard with over 25G. Let me briefly explain about the return loss. There are mainly two optical properties that are specified at the connection point of optical fiber: insertion loss and return loss. As you may know, insertion loss is the amount of optical power loss from sending side to the receiving side. If the insertion loss is large enough, signal is not transmitted to the receiving side. It causes communication errors of the worst case link down. I think this is easy to understand because signal does not reach that correctly. On the other hand, the return loss is the amount of optical power returned to the sender side at this communication point by reflections. It is unexpected situation and may cause trouble. it is hard to imagine how return loss affect the communication quality, so we've tested. The test environment used 100G LR4 transceivers and was configured to create sections with large return loss between connections. By creating multiple connections with the poor return loss, we built an environment in which the return loss could be adjusted to 21 dB or less, which exceeds the limit of specified value of transceiver. To check whether there were any difference depending on the transceiver manufacturers, we used transceivers from the 3 different companies for this test. We had interesting test result. First, we tested with adding the connection point which has a poor return loss under 21 dB, but the bit error didn't occur. This is just single connection point. Then we increased the number of connection points to 3. Then we found out that there is a bit error. This table shows the result. The bit error was confirmed in all 3 tests conducted by the different transceiver manufacturers. We guess it is caused by the multiple reflections. When the poor connection is only 1, the reflected signal at connection point goes only to the sender side. But when the poor return loss connection point is more than 2, the reflection signal at the connection point goes to the sender side and then reflected at this signal again to the another point. And the signal goes to the receiver side, and it repeats again and again between those ports. And the reflected signal goes to the receiver side together with original signals. The graph above is the normal eye pattern without multiple reflections. On the other hand, the lower graph shows the eye pattern in the environment where there are multiple connection points with multiple reflections. When there is multiple reflections, the waveform of the eye pattern becomes distorted and the line becomes thicker. This means that the waveform of the light transmitting 0 and 1 has been distorted. Multiple reflections disrupt the light waveform, resulting in the worsened bit error rate. We also tested whether the effect of the changing the optical power state when the multiple reflection occur. The top image shows the eye pattern when the optical power is at minus 1.1 dBm. The next image shows the eye pattern when the optical power is reduced to minus 6.5 dBm. At the same scale, the height of eye pattern is about 1/3 of the power, 1/3 lower than the image above. The bottom image shows the eye pattern when the optical power was reduced to minus 10.6 dBm, almost the lower limit for the optical transceiver. The height of eye pattern is even lower, and the eye opening is no longer visible when compared at the same scale. When enlarging the bottom image, you can see that the waveform appears a little hazy. As a result, the eye opening becomes narrower and the overlap at the intersection becomes thicker, which makes it easier for errors to occur in the 0-1 judgment. If you lower the input optical signal level significantly, the bit error will start to appear at a certain level, and the number of errors will continue to increase. In an environment where the multiple reflection occurs, the waveform is also disturbed by the reflections. So I think the signal level will be affected even more than under the normal conditions. This graph shows the received optical power versus the bit rate BR with the multiple reflection points. This is also an interesting result. Even if the power at the RX port is enough, such such as larger than -5 dBm, but bit error occurs. This is because the signal degradation by the multiple reflections. This phenomenon is unknown to our customer because received power is enough, but communication error occurred. This is a comparison of eye pattern of 3 transceivers. Even they are made with the same standard, the shape of the eye pattern is different between the manufacturers. The result of BER tests are different between the 3 transceivers also. This is an environment where the multiple reflections are present. We have confirmed that there are considerable difference in the performance between manufacturers in the environment affected by the multiple reflections. Here is a summary of the test result. We confirmed that multiple reflection caused by the interface in the transmitted light wave resulting in degradation. We also confirmed that as optical power level decrease, the impact of multiple reflection on the transmitted light increase. For this reason, optical fiber transmission paths with many optical connector connection points require caution. This is for your reference. For the 400G and above, PAM4 is the PAM4 on the right side of the right picture is the mainstream signal format. The testing we explained this time was based on the NRZ, mainly 100G with LR4. But with PAM4, the signal levels 0001, 1011 must be determined. The amount of signal that can be sent is doubled, but the signal level must be judged more sensitively. Here is another supplementary information. We've tested inserting pure return loss connection point into a long distance connections. The distance is 20 kilometers of each. In this case, we did not observe any bit errors, even if there are 3 pure return loss points. So longer the distance connection points, such as between like 2 red centers, it doesn't affect much. From the explanation so far, I hope you understand the multiple reflection causes communication errors. Before I talk about what causes them, let me explain the connection structure of the optical connectors. The image above shows the connection part of an LC connector seen from the side. The end surface of this connector is actually machined to be slightly rounded. The optical fibers are connected to each other with a force that is just enough to slightly crush the tip of it. Since this is a physical contact, it is easy to imagine what happens if dirt exists. As you can imagine, dirt will deteriorate the optical characteristic. We think the majority of the problems in the optical network caused by the contamination of the end face of the optical connectors. We often ask how much of an impact do they actually have. So I will explain the result of a test to see what happened where the dirt on the end face of an optical connector. On the left side, there is a reference value for the clean end face. The middle shows the data when the hand oil were applied. Hand oil were applied to the optical connector end face by touching them with the hand. As you can see, there is a slight decrease in the optical characteristics. And also, when the connector through is clean, when it's connected, but the dirt will transfer to the clean connector connection as well. So make sure both are clean before connecting it. And next one, the right slide shows the data when the dust was applied. The dust was applied by touching the connector with clothing. Both the insertion loss and the return loss are very poor, and you can see that it has a greater effect on the optical characteristic than the hand oil. Next, I would like to introduce some special cases that are not caused by the dirt. The first one is when connector is partially inserted. If the connector is not inserted all the way, the reflection will be extremely large. As shown in the illustration of the upper right, multiple reflection occurs in the air layer between the connectors and end face, which amplifies optical power and generate return light. To prevent this, it is important to always hear and feel the click. Another special case is that problem with the polishing grade of the optical connector end face. As shown in the table, optical connector end face are graded, and grades that are usually used are SPC polished or UPC polished at -40 dB or higher, which result in a clean end face like the picture 1. Connector number 2, on the right side of it, it's the picture of the right side of the picture. It is a connector end face made more than 20 years ago. The PC polished grade on the table. This picture is a little small, so it's maybe difficult to see, but the surface of the end face has many tiny scratches. As shown in the table, the PC polished grade has return loss of -25 dB. So naturally, the return loss at the connection point will be poor. It is unlikely that recently purchased optical cable will have this kind of end face conditions, but it is possible when reusing the cable that has already been installed a long time ago. So we previously received a consultation from the customer who had migrated from 10G environment to 100G. When we checked at the site, we found several areas with a high reflectivity, but they were not dirty. The cause was the polishing grade. The problem was solved by repolishing and upgrading to UPC grade. In the case like this, it is important to know the problem cannot be identified only by measuring the optical power level. As you can see, the various problems can be occurred at optical connector connection points. The way to prevent the resolved optical connector and face problem as explained above is to first inspect the optical cleaner and end face before connecting. Check the end face and clean it if it's dirty. If it is a scratch or has an old polishing grade, as explained earlier, you can restore it by polishing it. Polishing may seem difficult, but there are handy polishing machines available nowadays. So polishing is now easily possible on site. So don't give up if you have an optical connector with an old polishing grade, which hard to replace. Although it may be difficult to check all the end faces with a dedicated machine, so always clean the end face and optical connector before connecting it. That could make a big difference. Sometimes checking the optical power level alone is not enough to identify the problems. If you are in an environment where the communication error occurs, even though the optical power level is fine, try using measurement instrument called OTDO to check the conditions of transmission path. And OTDO is a device that sends optical pulse into the path and graph the conditions of the optical transmission path from the return time and the return of the optical power. As shown in the figure, the large peaks occurred at the point of reflection, making it possible to pinpoint locations where particularly large reflection occurs. So I think it's kind of early, but the next slide will be my last slide. And I would like to say that I'm wearing a tie because of. Just wanted to say that joke. Okay, so remember that multiple reflection can be cause of the communication errors. And also remember that measurement of the power level alone may not solve the problems. And always clean optical connector before you use it. Thank you very much.
Thank you very much, Takaya, for this very interesting talk here at DENOG.
Sorry, I was talking a little too fast. I'm sorry about that. I was so nervous. I'm not really used to talking to you.
We are very happy to have you here. Are there questions for Takaya? So obviously you explained very good.
Thank you. Thank you.
Oh, there is one question for you.
Oh, really?
Don't mind, he's a good one.
Hopefully, yeah.
Hello, Gerd Döring. I work for a data center company. Thank you very much for that talk. I will use it as training material for our on-site people because they don't believe that cleaning stuff is important.
Oh, okay.
Now they can see. Thank you very much.
Thank you.
And please remember, don't wear the tie when you go into the data center.
And remember me as a guy with a tie.
We will. Any more questions for that? Yes, there's another one. Now they are warming up, which is a pity because everyone else is waiting for the coffee.
Okay, Ulrich Just in Frago. Does fusion splices and mechanical splices have a similar impact? So meaning if you have too many of them in, that with the higher frequency ranges you have more influence and distortion?
It's hard to say. Probably keep it clean and check the cables, the connection points, and will be the option. But thank you very much, though.
Okay. If there are no other questions, then have a warm applause again for Takaya Nakagawa.
Thank you.